Corrosion is an insidious and pervasive phenomenon that costs the Department of Defense billions of dollars a year in direct costs. Corrosion negatively impacts military readiness, safety, logistics footprint, and the budget. Corrosion is a problem that all of us confront every day. Hi, I'm LeVar Burton, and you may know me from programs like Corrosion Comprehension, Combating the Pervasive Menace. And today, we are going to tackle another important subject: ceramics and how corrosion affects them. Although it is true that ceramics don't suffer from electrochemical corrosion, they are susceptible to degradation due to the environment. Ceramics are used for many advanced engineering applications, so their degradation often leads to serious results. So, what exactly is a ceramic? Well, they are physically non-metallic and chemically inorganic. Metals are made up of a nucleus containing protons and neutrons. The nuclei share their outermost electrons, and as a result, they are typically good electrical conductors. Organic materials contain carbon and hydrogen. Organic chain bonds most often result in materials which are insulators but can also be conductors or semiconductors. Ceramics include metal oxides, nitrides, carbides, and borides. They may be crystalline glassy materials and are also resistant to acids, bases, and chlorides, which tend to rapidly rust metals. So for that reason, ceramics are often used as a coating on metals to prevent corrosion. An interesting fact about ceramics is that they have unique optical properties that can change from transparent to opaque and back again. We use this exceptional property within a pilot's visor, where it adjusts to light sensitivity automatically, darkening to blank out explosions or any direct bright light that could impair their ability to fly. Now, once the situation passes, the visor calibrates back to its normal range. In addition, they offer a wide variety of electrical and magnetic properties and are used for everything from high-temperature superconductors, porcelain insulators, computer chips, solar cells, and other semiconductors, an MRI, cell phone resonators, fuel cells, and the magnets on your refrigerator. So, ceramics are complex materials with a variety of properties that can be engineered for a number of difficult applications. The degradation or corrosion of these materials can affect any and all of its desirable properties. So, let's take a moment to see how ceramics are produced. Well, they are often mined from minerals in the ground, and by utilizing a variety of different processes, the raw materials are refined, ground into powders, and finally formed. Most ceramics are sintered in order to solidify the fired material and eliminate porosity. Because of the high temperatures and inertness of ceramics, and thus their resistance to corrosion, it is arduous, expensive work and requires a great deal of energy to accomplish turning a ceramic into a solid piece. This makes it necessary to show the cost versus need for the ceramic material. The manufacturing of parts out of ceramics is not as simple as the creation of a part from a metal material. Except for the case of glass, most ceramics are not melted in order to form a final product. Processing, or the making of a ceramic part, is very energy intensive. A high temperature operation is necessary to make most ceramics, and that tends to be expensive. Now, one of the chief issues with ceramics is their lack of ductility and toughness. Unless engineered properly to avoid misfit, impact loading, dropping, etc., ceramics can fail unexpectedly and without warning. Ductility is the ability of a material to withstand bending without breaking. For example, you can bend and unbend a paperclip made of metal, like this, but if you try to bend a chalk, which is made from ceramic, it will shatter. Toughness is another important material's property. It's a measure of a material's ability to resist impact loads and cracking. To illustrate the strength and brittleness of ceramics, let's take a look at Prince Rupert drops. These are made by dripping hot molten glass into cold water. The glass is rapidly cooled and forms into a drop with a tail. The rapid cooling of the molten glass tempers the glass, putting the surface into compression and the interior of the glass into tension. The large compressive stresses in the head make the glass very strong and tough. The head of the drop can't be broken even with a hammer, while simply bending the tail will cause the glass to disintegrate. In order to better understand ceramics, let's turn our attention to look at why metals are used in specific situations where ceramic materials would fail. Metals are ductile, tough, and used in many mechanical systems. The ability of metals to deform without breaking means that even large gaps can be accommodated in machines made with moving parts, and toughness allows metals to withstand occasional impact loads. If you've ever looked closely at your washing machine, you know that the mechanical setup is not exactly perfect. In addition, the floor may not be level. Screws loosen over time, and there's certainly opportunity for corrosion. Occasionally, the machine goes off balance and starts vibrating, taking a disconcerting, clunking walk across the room. Now, think about what's happening here. This can't be what the designer had in mind. There are very high vertical and horizontal stresses, including unpredictable impact loads, but somehow the washing machine isn't in hundreds of pieces, and more surprisingly, it works fine the next time you turn it on. The ductility and toughness of the metals makes the machine forgiving of design errors, fit-up errors, and unusual service conditions. In the same way that metals help keep this washing machine together, metals also make it possible to drive your car through that big pothole without having your wheel come off, or your engine break up into 1,000 pieces. Unlike the graceful, slow failure of metals, catastrophic failures tend to occur quickly within ceramics, even though they are high-strength materials. We know that strength is a measure of the amount of load a material can withstand without failing. Using ceramics in a compression situation makes them stronger than metals, even though they are still frail in moments of tension. Concrete is a ceramic composite material. When concrete is loaded under compression, the failure initiates at the bulging free surfaces. In fact, every ceramic failure under slow loading is associated with low tensile strength, even under compressive loading. One way of combating this type of failure is wrapping concrete columns, which is a common earthquake retrofit technique. In addition to providing strength and preventing projectile damage, the wrap prevents the outside of the columns from failing in tension. So, what would make the perfect engineering material? Well, it would be a material that is very strong, tough, ductile, lightweight, and cheap, too. Unfortunately, there is no such thing as the perfect engineering material. In general, the stronger the material is, the less ductility it has. The low ductility is associated with cracking and catastrophic failure. Now, this is true for high-strength metals, polymers, and ceramics. Thankfully, there is a tremendous amount of research and development going on, including many nanoscience efforts, which are focused on making materials both strong and tough. Another characteristic of ceramics is that they are electrical insulators, and that means they don't corrode like metals. Ceramic insulators don't allow the flow of electrons through a galvanic cell. This is the mechanism that explains why metals corrode. So, when they are galvanically connected to dissimilar materials, there is no flow of electrons and no galvanic corrosion. In some cases, protective oxide films can naturally form on the surface of metals. Examples include the patina that forms on copper and the protective films that form on stainless steel, aluminum, and other alloys. Man-made protective and insulating films, including paint and anodizing, are some of the most important and widespread forms of corrosion control. Ceramic materials can suffer from a number of variable types of attack. First, these materials are soluble in some environments, whereby different ceramics can be dissolved by strong acids and bases. Solubility can involve all the ceramic particles, also known as grains. These processes can weaken ceramic materials, affect transparency, and affect other properties as well. Let's take a moment to speak to Dr. Gary Fishman, a renowned ceramics academician, to find out more about the possible degradation of ceramics.
Ceramics, like anything else, degrade in environments, and whenever you put it into something, it's in an environment. If you want to take an extreme example, take something like salt, which in its own way is a ceramic. You put it in water, and what does it do? It dissolves. Ceramics are like that. If you take the example of the salt again, each salt particle is a grain. And if you put a bunch of grains together, you make a real part. Well, the spaces in between those grains are more soluble than the actual grains themselves. They'll dissolve a little bit faster than the rest of the stuff. So what you find is that the ceramic itself, over the course of time in a fluid, is going to degrade at some level or another. Some ceramics will degrade very, very slowly, and some will degrade, like the salt, very, very quickly. Degradation can be a good thing. It can lead to things like bioactive ceramics. Bioactive ceramics and glasses are things that dissolve in the body, and the chemicals that dissolve from those glasses help the body actually build things like bone and muscle into the ceramic itself. A ceramic that you do not want to degrade is a ceramic that's used for, let's say, a hip replacement. In a hip replacement, you want that ceramic to stay intact, and you want it to stay smooth. There are other things that we use ceramics for. If you can imagine a heat re-entry vehicle, something like a space shuttle or a space capsule, when the space capsule comes back into the atmosphere becomes very, very hot, and it actually becomes what's called a plasma, which is a very high energy gas. That high energy gas can corrode, degrade, or anything else, a material very, very quickly. You want something as inert as possible so that the capsule itself will last. If the capsule surface is made out of ceramics, or the re-entry surface is made out of ceramic, it actually lasts through that plasma period until the capsule slows down enough that it can cool down and go down on its own without that protection. There are situations where we see degradation every day. In a situation like erosion, take the Grand Canyon, take the Monuments National Park over in the west. These are beautiful examples of erosion in which we have materials. These are ceramics, sandstone, limestone, things like that, that are being eroded over time and create these beautiful monuments.
Erosion is a mechanical process in which a flowing environment of gas or liquid removes the surface of a material. Next, corrosion of ceramics occurs in flowing environments where corrosion is accelerated by the effects of erosion. This process exposes new surfaces that can be more easily removed by the corrosive environment. Then, there are high temperatures at which even ceramics degrade at accelerated rates, ultimately suffering from oxidation, recrystallization, phase transformation, fluxing of material, and creep, which is the slow flow of a material under a load. Finally, let's take a look at some other forms of degradation ceramics suffer from, such as cracking and fracture, impact resistance, loss of specific properties, and change in dimensions. In fact, you could practically use ceramics for everything if they weren't so brittle and expensive to produce. But for those reasons, there are limits to where they can be used for corrosion control. However, let's look at some example applications where ceramics are the right material for the job. Making use of the protective oxide films that form naturally on valve metals, including stainless steel, aluminum, titanium, and niobium, is the basis for anodic protection. Now, under anodic conditions, the electrically insulating ceramic film that forms effectively shuts off the corrosion circuit. These films are not often thought of as ceramic, but they are, and they provide the primary corrosion protection to the underlying metal. Now, when stainless steel is coupled to mild steel in an aqueous environment, the stainless steel becomes a cathode, loses its protective oxide coating due to reduction, and eventually turns on the galvanic corrosion circuit. The stainless steel does not corrode because it is cathodically protected. On the other hand, mild steel coupled to stainless steel rapidly increases the rate of corrosion. More stainless steel only makes this problem worse by increasing the total cathodic current being pumped into a fixed area of anode. It's not a good engineering practice to use mild steel fasteners in stainless steel, The mild steel fasteners can fail within months, and the extra money spent on the stainless steel will have been wasted because it was not used under anodic polarization. Even using stainless steel bolts in mild steel structures can be troublesome in very aggressive environments. In this case, the mild steel around the bolt can be eaten away, leaving holes rather than fasteners in the structure. It is clear that design and review of corrosion basics, including anodic protection, to form and maintain a ceramic film when appropriate, is the best way to avoid unpleasant surprises with stainless steel, aluminum, and other materials that form protective anodic films. Also, anodized metals that are specifically treated to form a thicker and more stable protective oxide film are also commercially available. Now, there are other ways as well to use ceramics in galvanic cells, rather than using an insulating ceramic protective coating to protect the underlying metal. Ceramics that conduct electrons can be the primary components in electrochemical cells. These are specialized semiconducting ceramics that do conduct electrons. So these materials can be used to replace the metallic elements in a traditional corrosion cell. Semiconducting oxides can replace the anode, cathode, and electrical connection in the cell. The Army-developed ceramic anode makes use of semiconducting oxides as an anode material and provides long life and high protective currents. In addition, there are efforts to develop ceramic anodes for room temperature batteries, giving them much longer life than the current technology provides. Now, the concept of the electrochemical cell doesn't stop with the traditional aqueous corrosion cell. At high temperatures, water can't be used in a galvanic cell, but other materials can transport ions in the same way hydrogen plus 2 and chloride ions do. The high-temperature electrochemical properties of ceramics makes them useful for high-temperature fuel cells that can be used for electrical power in planes, spacecraft, and oxygen sensors such as those used in your car. Ceramics are excellent electrical insulators, but at temperatures above a few hundred degrees centigrade or 1500 degrees Fahrenheit, some ceramics like YSZ, yttria stabilized zirconia, become ionic conductors. At these temperatures, ions like oxygen plus 2 can be transported through ceramics like ions are transported through water at room temperature. So, ceramics can be used as the electrolyte in a now solid-state electrochemical cell, with solid metals or semiconducting oxides used as the anode, cathode, and electrical connection. Solid oxide fuel cells can be used for direct methanol conversion and a number of other applications. These cells are typically operated at temperatures of over 1,000 degrees centigrade, with solid electrolyte materials configured as sheets or tubes with coatings of electrode materials. Ceramics can be used alone or in conjunction with other materials, such as metals and polymers, in order to optimize the properties of the compound material. For instance, concrete is a ceramic composite material made from paste and aggregates. It depends on each component to provide strength and long life. The paste, composed of Portland cement and water, coats the surface of the fine and coarse aggregates such as sand and rocks. The paste hardens and gains strength to form concrete over days to weeks. In the case of the automotive catalytic converter, ceramics are used as the honeycomb structure that will ensure that the converter is structurally sound even in the very corrosive atmosphere of automotive exhaust. Here's a question. Have you ever asked yourself why a common household toilet is made of ceramics? Well, the answer is simple. Because it resists the corrosive substances that it constantly comes in contact with. In many situations, ceramics are used as a coating, just like paints, to keep the corrosion environment from attacking the structure. Some examples are as a corrosion-erosion mitigating coating on superheaters and power plants, as an enamel to coat steel, and as a calcium phosphate coating on dental implants, which are actually used in a pretty special way. They corrode, and during the corrosion process, they help the bone to grow up and into the dental implant. These incredible ceramic materials are also used for many military applications, including personal ballistic body armor, the sonar horn on a ship, the Air Force's coating that makes the stealth bomber stealthy, and radomes that guide missiles. Even spacecraft and the foam silica within it depends heavily on ceramics. And we can't forget energy. Many aspects of the energy and nuclear industries rely on ceramics. Uranium fuels used in many nuclear reactors are ceramic pellets of uranium dioxide, and ceramics are generally the material of choice for handling nuclear waste contamination. So, as you might expect, it's very important to select the appropriate materials for minimizing the corrosive effects of an environment. This can be done by altering the actual environment through design by utilizing cathodic and anodic protection or the applications of coatings and inhibitors. In conclusion, ceramics are a very important engineering material with many attractive properties and are very resistant to most corrosive environments. Better yet, they tend to degrade much more slowly than their metal and polymer counterparts. As a result, even if they are not used alone, they are often used in conjunction with a metal part to save it from the corrosive environment it might otherwise have to endure. Ceramics have been around for thousands of years, and you can expect them to be around for thousands more. And by viewing this very technical program on ceramics, you are becoming involved in combating corrosion. Until next time, I'm LeVar Burton. Thanks so much for watching, and remember, rust never sleeps.